Okay, so we're back to EXO. We're back to EXO 5, but this time around we are working on part B. We're working on part B, and part B says we have a language, L2. Now this language contains strings that are defined over this alphabet. The alphabet is A, B, and C. Then we do that. They're saying such that these strings end in A. Now, we see this language here, the language whereby all strings end in A. Which language is that? The simplest string in that language is A itself, because when I have a string that only contains A, it ends in A. So always when you're working with these infinite languages, why am I doing this? Because I want to do the automaton. For me to be able to deduce the grammar, I can start with the automaton. You get it? You can start with the automaton. Then from the automaton, you can simply find the language that you want to, the grammar that you want to deduce. So in here, when I have a language whereby all strings must end in A, the simplest string in that language is going to be A itself. So when I'm drawing my automaton, that's going to form my skeleton. So for my automaton, I'm going to say it as the starting symbol. I'm going to call it S. So since this is the starting symbol, I put this symbol to mean it is starting. Then when I see an A, I go to another state. But since A is in the language, when you see an A, you must go to an accepting state, and that accepting state is A. When I see an A, that is okay. Now what is interesting here is one. When you see an A, only A, the string is in the language because it ends in A. But after seeing an A, if you see more A's, that is okay because the string is still ending in A. For example, if I had a string A, it is in the language. If I had a string A, it is ending in A, it is ending in A. So when I see A, I'm staying in this accepting state. But here, at first, because the alphabet has three symbols, A, B, and C, it means that here, when I see a B or a C, I'm going to keep waiting because I want to find an A, because strings in this language must end in A. So when you see a B or a C, we step in this state, and this state is not accepting. So if the automaton, for example, a string of this kind here, B, C, B, we see a B, we come here, we see a C, we come here, and we see a B, we come here. So since after reading the whole string, the automaton is not in an accepting state, we say this string here is not in the language. You get it? But if I have a string like A, when I see an A, after reading the whole string, we're in an accepting state, so we say this string is in the language. The same applies to this and this, because when I see A and a number of A's, I just accept them. So we have this language here. So you may ask me what happens if we see a B or a C after here. If we see a B or a C, we must throw them to a trapping state. No, sorry. When we see a B or a C, we come back here and wait to see an A before we can come to this accepting state. So we have this grammar you are seeing here. So this is the grammar we have. This is the grammar we have. So what's going to happen is one, we have formed the automaton, and simply let me first recap on this automaton. The automaton accepts all strings that end in A. So when we see A, that is okay. But when I see a B or a C, before seeing an A, I don't go to this accepting state, because all the strings in this language must end in A. So when I see a B or a C, I keep waiting for an A. Once I see an A, I go to an accepting state. When I see more A's, they're all ending in A, so they're accepting. But when I see a B or a C, I go from this state and I come back to B and C to S, so to wait for an A. So when I try to write the grammar for this language, I'm going to come and say I have state S, I have S, and when I'm in S and I see A, I go to capital A. Or when I'm in S and I see a B, I go to S. Or when I'm in S and I see a C, I come back to S. Then we come to A. When I'm in A and I see an A, I come back to A. Or when I'm in A and I see a B, small b, I go to S. And when I see a C, I go to S. Now, but since this one is an accepting state, we can give us epsilon. Now you get it? Now what is interesting here is 1. Sometimes you must be careful. So, because this is the grammar we have got, this grammar is correct, but this grammar you are seeing here is not the same grammar as that they have in the solutions. A language can have different grammars, and they all can be correct. Now let me try to make it similar to what they defined in the Fichie solutions. Now, before we go this way, simply when you see this language that ends in A, we can say that language can start with anything. You get it? It can start in anything, and it must always end in A. So what I can say the grammar is simply this. When I have S, I can start with anything. I can start with A. The string can start with B. The string can start with C, but the string must always end in A. You see? Now this is the grammar they have in the solutions, and this grammar is the same as this one. You may ask me how comes. Now let me try to simplify this grammar so I can find this. But when you see this grammar, it says when you can start with A, you can take on anything, because when you see A, we have S. S can give us a B, S can give us a C. So the strings in this language can start with anything, A, B, or a C, or they can be only A. And we saw that A is also a language in this string. So this is the production rules they have in the solution. So I'm going to modify my grammar to come to this state here. So when you come back to this grammar, we see that A is giving us what? A is giving us a BS and a CS, but also S gives us a BS and a CS. You see what I'm talking about? So we can simply come and say, now, first of all, you see that in this production rules here, we're having epsilon. But let's face it, this language here doesn't contain epsilon, so you can remove epsilon from this language. But how do I do that? But I'm going to say A gives us epsilon, so we have this production rule in this language. You have A can give us epsilon, which means this is called a null production. Null, which means A can give us null, which is epsilon. So what I have to do is I can come and say, I'm going to rewrite these production rules. I come and say we have S was equal to capital A, small a, capital B, small s, capital S, that. Then I come and put this stroke. Then I'm going to replace with A with epsilon. Whenever capital A appears in this grammar, I'm going to replace it with epsilon, because A can give us epsilon. So when I come here, I replace capital A with epsilon, I get A. But we don't have capital A, so I leave it alone. So I can also come here and I say, now what about A? I first write all these boys as they appear. BS, CS. Now since A can give us epsilon, I come and I replace A. I get this. Don't write this again, because we are trying to get rid of epsilon, because this language you are seeing here doesn't contain, this language you see here doesn't contain epsilon. So this is also another correct grammar. This is correct. This is also correct. In the Q, they have this one. Now, when I come here, what is interesting? When I come here, I'm like, S gives us BS and S gives us CS. It is the same thing here. You see? So what I can do, I can come and say, but S gives us A and A gives us A. So the only thing we need from this A is this AA. But you see, this is A and this is A. So how can I remove this production rule here? I can bring and I throw it up here and I get a bigger one. I get S gives me this and gives me this. But since this is A and this is A, I can simply change them. I can simply say, because if I want to remove A from this grammar, this one, then I must also remove it from here, because we will not have a production rule for capital A. So the best way to see this is one. Capital A gives us BS, it is here. Capital A gives us CS, it is here. So, but this is capital A gives us AA. So this is a loop. You see, capital A, then small a, then AA. So simply I can come and say, this is already here, this is already here, and this is here. So I can only change this one. Instead of writing A, I write S. So I can get a grammar like S is equal to A. Instead of A, I'm going to write S because I want to use A again. S, then B, S, then C, S, then A. And intuitively, this is the grammar they have here. But this grammar simply says that strings in this language can start with only A. That is okay. They can start it with A, B, and C. But what is surprising is one. When you see this production rule here, the only way we can stop, this is recursivity. The only way, now this is the base case, a terminal. Terminal means to stop. When you see this production rule here, the only way we can terminate derivations in this language is by putting small a, which means all strings in this language are going to be ending in what? In small a. So this is a grammar which is correct. This is correct, and also this one is correct. But this one just comes from practice, because you see that all strings in this language must end in a. So the only way you can stop this loop, because we have s, s, and s, the only way you can stop this capital S is by putting a at the end. So all strings in this language must end in a. So the grammar for this case is the grammar. The alphabet is A, B, and C. So the terminals, that is A, B, and C. Then V, which we talked about, is the set of states, which is S and A. But since we have removed A, we can also just use this. You get it? Because our grammar now has only one state. So we began from here, but we have simplified the grammar to something like this. You get it? Now we have the starting point, which is S, and my production rules are just AS, BS, CS, and A. Now this is the grammar. Now you may ask me a question that, hey, but first wait, young man. The grammar we have here is this, you see? But now, you see, this grammar is not the same as this grammar, because this grammar says we can start with A, you see? Now it is interesting that also, you see this grammar also, this language here doesn't contain epsilon, so you can remove epsilon by doing what? We can come and say A gives us epsilon, which means A, we have this variable A can give us epsilon, so which means A is a null production. So I'm going to write this grammar as it is. Come and say S is equal to capital A. This, then I do that. Then whenever I see capital A, I replace it with epsilon, so I get A. Then I come to the second A. I first write it as it is. See, and now don't put the epsilon because you're trying to get rid of it. So I come and I replace. Whenever I see capital A, I put epsilon. So I get, for this one I get A. For this one I get B, and for this one I get C. So this grammar you are seeing here is the same as this grammar, but this grammar is called K grammar. This is a K grammar. This is just a general grammar. So you get it. So in this grammar you don't have any epsilons because this language doesn't contain epsilons. I think this makes sense.